Hi, good evening, everyone. Myself, Avinash, Assistant Professor, Department of Pharmaceutical Chemistry from CMR College of Pharmacy. For the next 15 to 20 minutes, I'm going to talk on Clemmenson Reduction, which is another important reaction of synthetic importance. So we'll discuss this Clemmenson Reduction. Right. So before we discuss the general reaction mechanism of Clemmenson reduction, first, I will make you understand what exactly Clemmenson reduction means, what it is about. Okay, so if you see the normal statement for Clemmenson reduction, it is nothing but the reduction of carbonyl groups of aldehydes or ketones to corresponding hydrocarbons or methylene group in the presence of zinc amalgam and concentrated HCl. Okay, so better I will write zinc amalgam and excess concentrated HCl. So this reaction you can call it as Clemmenson reduction. So in Clemmenson reduction, what happens exactly? It is concerned with the reduction of carbonyl groups of aldehydes or ketones to corresponding hydrocarbons or methylene group. You know, the general formula for methylene is CH2. Hydrocarbons generally include your carbon or hydrogen atom. That is combination of carbon and hydrogen is nothing but your hydrocarbon or methylene group CH2 in the presence of zinc amalgam and excess concentrated HCl. Okay, so that is you are going to convert a carbonyl group into a hydrocarbon or a methylene group. Such type of reaction, you can call it as Clemmenson reduction. So if you see the general reaction of Clemmenson reduction, so I will take, so you can take any carbonyl compound, whether it is an aldehyde or you can take a ketone, doesn't matter. Okay, this I'm going to react with zinc amalgam in the presence of concentrated HCl. So you are going to get CH2, okay, where generally R represents your alkyl groups here. Okay, so with this you should understand what might be the reaction here. So what is happening exactly is, if you look at see, this is your carbonyl group, right? Ketone. So this ketone functionality has been converted into methylene group, CH2. So you know, reduction is nothing but removal of oxygen and addition of hydrogen atoms. That process you can call it as reduction. So this can be done in the presence of zinc amalgam and concentrated HCl. So you may get a lot of doubts now how this ketone functionality or how this carbonyl group has been converted into CH2. So this we can understand clearly if I explain the mechanism of action, mechanism of Clemmenson reduction. Okay, so now I'll try to explain this mechanism to convert the carbonyl group into hydrocarbons or methylene group. Okay. So I'll erase this everything here so I can explain the mechanism very clearly. Right. Now what is my objective is I should be able to explain you how to convert a carbonyl group into a methylene group, that is CH2. That is what we have observed in the reaction now. Okay. So coming to the mechanism of the reaction. Right. Now first, I will write the general structure here. What is this? This is a carbonyl functionality. So I told you just now, you can take anything. You can take aldehyde or a ketone. Okay. And here oxygen will have 2 lone pair of electrons. So this carbonyl compound, I'm going to react with hydrochloric acid. So when hydrochloric acid dissociates, you will get H plus and Cl minus. So this oxygen will abstract this hydrogen atom by donating a lone pair of electron. Therefore, what happens? A new bond will be formed between oxygen and hydrogen. Okay, so oxygen is going to abstract this hydrogen atom, okay, by donating the bonding electrons with oxygen. Therefore, this oxygen will form a new bond with hydrogen. Okay, so this is generally called as a protonation step. Here you will get OH, okay, R and R dash. But here oxygen will have only 1 lone pair of electron with a positive charge, because when oxygen donates the lone pair of electrons for hydrogen, you will get only 1 lone pair of electron with oxygen. So it is deficient with another lone pair of electron. So you can designate by a positive charge. Okay, so this is nothing but your protonated carbonyl group. Okay, next. What is the problem with oxygen here? Oxygen is electron deficient. It requires electrons. So you compare the electronegativity between carbon and oxygen. As oxygen is more electronegative, the bonding electrons which is present in this pi bond will shift towards oxygen. Therefore, oxygen gets, you can write here. So when these pi bond is shifted towards oxygen, you will get only single bond here, followed by oxygen with 2 lone pair of electrons, hydrogen, R, R dash. Okay, so just due to the electronegativity difference, the bonding electrons will migrate towards oxygen. So oxygen will get two lone pair of electrons with a single bond with carbon. Okay, now whenever you shift this pi electrons towards this oxygen, what happens to carbon here? Carbon will get positive charge. Okay, why carbon got positive charge here? As the pi electrons are shifted towards oxygen, carbon gets electron deficiency. Okay, so the same positive charge I have written here. So this is nothing but your carbocation. So this carbocation can be stabilized by using zinc. So zinc usually contains the valence electrons. Okay, so in the next step, what happens? Here, oxygen will have the same thing, R dash. Okay, this positively charged. So these electrons will migrate towards carbon. Okay, therefore, what happens? The carbon will get the lone pair of electrons. Okay, so the carbon will get lone pair of electrons here, and you can designate it by a negative charge. Okay, so as carbon is electron deficient and unstable, to make it stable, I'm using zinc, okay, which has the valence electrons. So zinc will transfer the electrons for this positively charged carbon. Okay, therefore what happens? Carbon will get the lone pair of electrons. Better if I designate this arrow mark towards then you can understand very easily. Okay, so zinc is going to donate the valence electrons towards the positively charged carbon. Therefore, you are going to get the lone pair of electrons on the carbon atom. Okay, so you can designate by a negative charge. Okay, so next, you can treat with HCl. Again, HCl will undergo dissociation to form H plus and Cl minus. So carbon will donate the lone pair of electrons for this hydrogen. So therefore, what happens? This carbon can form a new bond with hydrogen. So you can write carbon OH. This is a R and R. So this is a new sigma bond which is formed between carbon and hydrogen. How it is formed? So whenever you use this hydrochloric acid, it will undergo dissociation process to form H plus and Cl minus. So this H plus will be abstracted by this carbon by donating its electrons. Okay, therefore carbon will form a new sigma bond with hydrogen. Okay. Next, okay. So if you use another HCl molecule here, okay, already one HCl molecule I have utilized. If you use another HCl molecule, what happens here now? So it will undergo dissociation once again to form H plus and Cl minus. So here oxygen usually have two lone pair of electrons. So these lone pair of electrons will be shifted for the positively charged hydrogen. Therefore, what happens? This oxygen will form a new bond with hydrogen. So here you will get a carbon, and instead of OH, you can write OH2 with one lone pair of electron and a positive charge. And here, as usual, hydrogen, R dash, and this is R. Okay, so you're having positive charge with oxygen. as it is having only one lone pair of electron here. So in the next step, what happens? Dehydration takes place. What is dehydration? Removal of water. How can you remove water? If I break the bond between carbon and oxygen. So what happens if you break the bond between carbon and oxygen? The electrons will come out and migrate towards oxygen atom. Okay, why? Because unless and until oxygen gets two lone pair of electrons, okay, the water can be eliminated out because oxygen gets this stability. So when I break the bond between carbon and oxygen, as oxygen is more electronegative, the electrons will migrate towards oxygen. Therefore, oxygen gets two lone pair of electrons and entire water molecule will be liberated out. Okay, therefore, what happens to this carbon? Carbon will get positive charge. So you can write R carbon H R dash. What is the charge on this carbon now? Carbon will get positive charge. So in the next step, you can use HCl again. So this HCl will undergo dissociation to form H plus and Cl minus. So this H plus, so better instead of H plus, you can use zinc here because we need to stabilize this carbon first. Okay, so I will try to use zinc, which contains the bonding electrons. So these bonding electrons will be shifted to this carbon atom, which is having positive charge. So you will get R carbon with lone pair of electrons, hydrogen, and R dash. In the next step, you can use HCl, which will undergo dissociation to form H plus and Cl minus. So this H plus will be abstracted by this carbon atom, which contains the lone pair of electrons. Therefore, there will be a new bond formation between the carbon and hydrogen. So you will get C, H. Here also you'll be getting another hydrogen. This hydrogen I've written here. And this is a new hydrogen which is formed when the carbon abstracts the hydrogen atom by donating the bonding electrons. So here you will get R dash and this is R. So this is how the carbonyl group, this C double bond O, has been converted into CH2. So this is nothing but methylene group. Okay, so this is a mechanism for your Clemmenson reduction. So we have completed Clemmenson reduction, the general statement, reaction, and the mechanism. So in this mechanism, you can understand how this carbonyl group has been converted into CH2. Okay, thank you.